Everyone. Welcome to the Prague Mathematical Physics Seminar. Our speaker today is Tommaso Macrelli from ETH Zurich, and he will tell us about homotopy algebras and color kinematics duality.
Hi, everybody. Yeah, thank you for the opportunity to give this talk in online mode. It was, the initial idea was to be there in Prague, but that was not possible for me. So I'm still happy to do that online. So in this talk, I will discuss some aspect of color-kinematic duality and how they can be interpreted in terms of homotopy algebras. In particular, I will discuss how to bootstrap three-level color-kinematic duality to a generalized notion of color-kinematics duality valid for loop level. And I will interpret that in terms of homotopy structure. This is based on joint work with my collaborators, Liron Borsten, Brano, Jungro Kim, Christian, and Martin. So let's start with an old story. So let's consider Puyang's theory that we all know, and let's consider the fundamental field of this theory, that is the gauge potential. Gauge potential is labeled by two indices with very different meaning. First, we have the color index that manifests the internal symmetry described by a finite dimensional algebra. And then we have the Lorentz index that manifests space-time symmetry, Poincaré symmetry of a theory. And inspired by Coleman-Mandula theorem, we may be tempted to say that these two indices have nothing to do with each other. More precisely, Coleman-Mandula theorem says that the most general symmetry algebra that leaves the S matrix of a quantum field theory invariant under some assumption, that is, we want the symmetry to contain Poincaré algebra, or we want a finite number of particles with mass less than m for every positive m, and some assumption of the analyticity of the S matrix and other assumption. Then with these assumptions, we have that the most general symmetry algebra that we can have is the direct sum of the space-time symmetry algebra, Poincaré algebra, with some finite dimensional Lie algebra. So space-time symmetry and internal symmetry cannot combine in any but the trivial way. So we may be tempted to say that space-time index and color index have nothing to do with each other. A modern perspective on gauge theory apparently challenges this result, saying that actually space-time index and color index have something to do with each other. They are precisely on the same foot. And this perspective is provided by color-kinematic duality. Now, let's consider, again, Puyang's theory, and let's consider a generic endpoints loops amplitude in this theory. We can write this expression in this form. Here we have a sum of trivalent graphs. Yes, a caveat to this representation is that we are summing over trivalent Feynman graph. Practically, we do this blowing up the 4-point interaction vertex of Young's theory into trivalent contribution that we split into the trivalent interaction channels. Then here we have some symmetry factor. Here the denominator comes from the denominators of the propagators, and the numerator splits into two pieces. First one is color factor that is composed of gauge group structure constant. Second one is the kinematic factor that is Lorentz invariant contractions of polarizations and momentum. Now, given scattering amplitude, this decomposition does not follow in a unique way. we have some freedom in the choice of kinematic factor. This goes under the name of generalized gauge freedom. So we can shift the kinematic factor by some delta that satisfy this relation. And we see if we plug this generalized gauge transformation into this expression, we obtain the same amplitude. And this freedom in the choice of kinematic factor lies at the heart of the following statement. That is color-kinematic duality as originally formulated by Bern, Carrasco, and Johnson. So there is a choice of the kinematic factors, just that they obey the same algebraic relations of the corresponding color factor, namely antisymmetry and Jacobi identity. Now, this was proven to be true for tree level, but only conjectured for loop level. And if this was true also for loop level, then it would allow us to do something really powerful. That is to compute gravity amplitudes from Yang-Mills 1. And this is what goes under the name of double copy prescription. So if color-kinematic duality holds true, then if we replace the color factor in our factorization of Yang-Mills amplitude with a copy of kinematic factor, then we obtain a new expression that is precisely a gravity amplitude, more precisely an amplitude from n equals 0 supergravity theory. That is the theory with the Einstein-Hilbert gravity, Karl-Bramont field, and the dilaton. Just a question, can you hear me well?
We can, yes.
Okay, perfect. Thank you for the feedback. So this double copy prescription is a null loop statement. That means that to validate that for the loop level, we need the loop level validity of color-kinematic duality. And this is in principle something difficult to prove. Until now, what I exposed was an on-shell scattering amplitude story. Our approach is to bootstrap this scattering amplitude description to an off-shell Lagrangian realization of color-kinematic duality and the double copy prescription in order to solve the all-loop problem. And we will see that homotopy algebras provide a natural description for this action-based description of color-kinematics duality and double copy. So I suppose that everybody here is more or less familiar with homotopy algebras and BV formalism. So this would be just a fast recap of homotopy algebras related stuff. So homotopy algebras are generalizations of classical algebras. To obtain the homotopy generalization of our favorite classical algebra, we pick its structural identity, and we say now that this identity is violated, and this violation is controlled by an homotopy. For example, if we want to generalize Lie algebra to its homotopy algebra generalization, that is L infinity algebra, we pick Jacobi identity, and we require that its validity now is that it is violated, and this violation is controlled by an homotopy. So Jacobi identity holds up to homotopy. So homotopy algebras are more or less everywhere in physics. For example, L infinity algebras are the algebraic structure of classical closed string field theory. And under every Lagrangian field theory, we have an L infinity algebra that encodes all the classical theory, symmetries, fields, equation of motion, all encoded into this L infinity algebra. And the bridge between the L infinity algebra and the field theory is provided by Batalin-Vilkovinsky formalism. So BV formalism was developed to gauge fix and quantize complicated gauge theories. For example, if we have a higher gauge theory where the gauge parameter, the ghost that we introduced to parameterize gauge freedom, may enjoy themselves gauge freedom mediated by higher ghost. If we want to quantize higher gauge theory, then BST formalism is not enough. And we need to use Batalin-Vilkovinsky formalism. So this is because in general, for higher gauge theory, the symmetry of the theory does not close off shell. So the BST complex is a complex only up to equation of motion. And for quantization, we need an off-shell complex. So the first Batalin-Vilkovinsky quantization is a two-step procedure. In the first step, we parameterize gauge freedom just like we do in BST formalism. So we introduce ghost to parameterize gauge freedom, and eventually, in case of higher gauge theory, higher ghosts. Then we double the field content of the theory. We end up with a structure that is a cotangent bundle, where the BST fields are the local coordinates and the antifields are the fiber coordinates. This comes with natural symplectic structure and Poisson bracket that we use to generalize the old BST object. We generalize the BST operator and the BST action to a new BV operator and BV action. And in particular, we require the last equation here, that is a generalization of the notion of gauge invariance for the action. And this is called the Batalin-Vilkovinsky classical master equation. Now we have a differential algebra. We have in particular a differential complex in terms of the BV operator of shell. And this differential algebra dualizes to a codifferential coalgebra that can be described as an L-infinity algebra. And here is the link with homotopy algebras. But before discussing the dual picture, let's just conclude the discussion on the quantization. For quantization, we need some gauge fixing condition, and that in the BV formalism means to evaluate the action on an appropriate Lagrangian submanifold. In practice, we do this introducing a gauge fixing fermion and eliminating the unphysical degree of freedom, the antifields, taking functional derivative of this gauge fixing fermion. Then we impose a generalization of the BV classical master equation, that is the BV quantum master equation, that guarantee gauge independence for the expectation values of the observables. So this is just a recap of the BV quantization procedure. So first step is the BST complex. So we introduce ghost and eventually high ghost to parameterize gauge freedom. Then we double the field content of the theory. And then we are ready to introduce some gauge fixing fermion to gauge fix, and then quantize the theory. So as I said, let's jump to the dual.
Can I ask a question?
Yeah, sure.
Hi. So you said that BRST is not enough because the algebra closes on shell only.
Precisely.
And somehow BV should help me to set things straight, right? But once you gauge fix, once you express those antifields in terms of the gauge fixing fermion, you're pretty much in the original BRST gauge fixed form, right? So aren't you having the same problem as before when you would just do the BRST procedure?
Well, the BV formalism allow us to use more a wider range of gauge fixing. And yeah, I summarized the procedure here in only a few slides, but actually the discussion would be a bit more complicated on how we fix the gauge. Actually, yeah, the problem, as you said, is that in the case of higher gauge theory, we have symmetries that close only on shell. This is not a problem for standard gauge theory, where the BST complex is a complex also of shell, for example, for Yang-Mills theory.
Okay.
Thank you for the question. So, yes. So BD formalism, but also BST formalism, introduce a differential operator, introduce a differential on the algebra of polynomial functions of the field. This is an example of a more general construction called Q vector spaces. The simplest example is that of an ordinary vector space with some basis, and the most general degree 1 differential that we can write has the following form, where this psi are the basis for the dual vector space. So the differential is completely given in terms of this structure constant FABC, requiring that q squared to 0 now is equivalent for the structure constant to satisfy Jacobi identity. And so requiring q squared to 0 is the same to require that we have a Lie algebra structure with bracket given in terms of the structure constant. So this can be seen in a very convenient way, introducing objects called contracted coordinate function that are just the tensor product between the dual basis and the original vector space basis. We have that Q acting on this contracted coordinate function, act on the dual basis, and this is given by this expression, the action of Q on the dual vector space basis, and this dualizes on the original vector space in terms of Lie brackets. Now, in the most general case, we have a graded vector field, and we write in the same way contracted coordinate function, and in the analogous way, we dualize the action of Q, that in this case is the Batalin-Vilkovinsky operator, on the contracted coordinate function. This time, Q dualized not to Lie brackets, but to a sum of multi-bracket that are multilinear and graded antisymmetric. We call them higher products. And requiring that q squared to 0 is equivalent to require that the higher products satisfy the structural relation of an L-infinity algebra. That is, they satisfy generalization, an homotopy generalization of Jacobi identity. So an L-infinity algebra is a graded vector space equipped with higher product, and they satisfy this generalization of Jacobi identity. And as we have seen, Batalin-Vilkovinsky formalism associate to every Lagrangian field theory an L-infinity algebra. Now, let's be a bit more precise. So we have a Z-graded vector space, and we equip this graded vector space with a differential of degree 1. So we have a chain complex, and we equip this chain complex with the higher product, and we require them to satisfy the homotopy Jacobi identity that has this form here. So the first three identities are can be written as follow, and they simply means that the first higher product is a differential, and we have Leibniz rule between the differential and the two bracket. And the third one maybe is the most interesting, because the left-hand side is just Jacobi identity, and this is not equal to 0, but it's violated Jacobi identity, and the violation is controlled by the 3 bracket mu3. So we call the graded vector space equipped with this higher product an L-infinity algebra. We have also generalization of associative and commutative associative algebra constructed in the same way, and they are A-infinity and C-infinity algebras. We have a notion of morphism between L-infinity algebras, and morphism are a collection of linear totally graded antisymmetric maps that respect the higher product structure of the two L-infinity algebras. In particular, the first map, that is a map between one graded vector space to the other. If that map is invertible, then we have what we call an L-infinity algebra isomorphism. For our purposes, the notion of isomorphism is too strong. And indeed, the right physical notion of equivalence at the level of L-infinity algebra is given by quasi-isomorphism. We say that a morphism is a quasi-isomorphism if the first map, phi1, induces an isomorphism at the level of the cohomology rings of the two L-infinity algebras. Next, we introduce a bilinear pairing, kind of inner product, that is the cyclic structure. And we require this bilinear pairing to be cyclic in the usual sense, modulo signs coming from the graded nature of the objects. Yes, signs everywhere comes from the graded structure of the graded vector space. So the general template that we use to translate a field theory into something that we can read the L-infinity algebra directly off is Maurer-Cartan homotopy theorem. So given a cyclic L-infinity algebra, we call a degree 1 element a gauge potential with a clear physical reference. And we can define also curvature that generalize the usual notion of curvature that obey a generalization of Bianchi identity. Now we say that the gauge potential is a Maurer-Cartan element if its curvature is 0. And this equation is an equation of motion. It comes from a variational principle if we have the following action that is called the Maurer-Cartan action. Here the angular brackets are the cyclic structure, mu I are the higher products, and from this action, from minimizing the action, we obtain the Maurer-Cartan equation. And infinitesimal gauge transformation for this theory are mediated by the degree 0 element that we call ghost. And they may enjoy themselves gauge freedom mediated by next to lowest gauge parameters that are the higher ghost. So this framework is particularly useful to discuss higher gauge theory. So let's, for example, consider Yang-Mills theory, pure Yang-Mills theory. So this is the Batalin-Vilkominski action for Yang-Mills theory. We extended the action introducing antifields. This is an anti-gluon, this is an anti-ghost, and other field that we call trivial pairs. Now, the interpretation of trivial pairs is a bit less direct. As I said, to gauge fixer theory, we need a gauge fixing fermion. That is a degree -1 field. And to define this gauge fixing fermion, we need additional field content that should not spoil the BV complex, and in this sense should be trivial. This is precisely given by trivial pairs field. So we can formulate this theory as a Maurer-Cartan homotopy theory associated to some cyclic L-infinity algebra. And the L-infinity algebra of Yang-Mills theory is the following one. This is the chain complex for the L-infinity algebra, so this is the differential. So we see ghost mapped to gluon, mapped to anti-gluon, mapped to anti-ghost, and trivial pair field are trivially mapped with the identity into each other. And then we have higher products and cyclic structure. And the Maurer-Cartan homotopy theory associated to the cyclic L-infinity algebra is precisely this Batalin-Vilkominski action for Yang-Mills theory. So as I said, let's gauge fix. So let's introduce gauge fixing fermion. In particular, we will work with this family of gauges parameterized by a real parameter xi. The gauge fixed action reads as following. So this would be your setup for Yang-Mills theory. So some definition and some result for L-infinity algebra. We say an L-infinity algebra is minimal if the differential is 0, and we call an L-infinity algebra strict if it has only the first and the second higher product, that is, if it is a differential graded Lie algebra. And we have two useful structural results for L-infinity algebra. The minimal model theorem that says that every L-infinity algebra is quasi-isomorphic to a minimal L-infinity algebra, and the strictification theorem that says that every L-infinity algebra is quasi-isomorphic to a strict L-infinity algebra. And this, in particular, at the level of field theory, can be interpreted in the fact that every Lagrangian field theory can be formulated as a theory with only cubic interaction. And in the following, we will see a practical example on how to strictify field theory. So let's return to color-kinematic duality. And as I said, let's see how we can bootstrap a three-level color-kinematic duality, the loop level. So to precise the notion of color-kinematic duality that we want to discuss, let's say that loop integrand are not physical quantities. Indeed, if we perform a filter definition, loop integrand in general will change. So the precise notion of color-kinematic duality we are interested in for loops is the following one. We say that a theory described by some action satisfies color-kinematic duality if its action is weakly semi-classical equivalent, that is the same up to field redefinition and with the introduction of auxiliary field, to an action such that the associated Feynman diagram expansion produce CK dual loop integrands. So this would be our notion of color-kinematic duality. So let's start the bootstrap procedure from three-level color-kinematic duality to loop-level generalized color-kinematic duality. So we start with a theory that is color-kinematic dual at three level. And we select a color-kinematic dual parameterization of three-level scattering amplitudes. Now, suppose that the action that we have for this theory generates color-kinematic dual parameterization up to n-1 point. Then, in general, adding vanishing terms, we can obtain an action that generates the wanted color-kinematic dual parameterization up to n point. And we will see that in general, the action that we obtain is non-local. So this is an example of this abstract procedure that is, again, Yang-Mills theory. So this is a known result for Yang-Mills theory. Comes from Bern, then and Huang, Kramer, and was later developed by Torotti and Weinzel. So Yang-Mills theory can be described by a non-local Lagrangian of this form. This is an infinite sum of terms. The first four terms are precisely standard Yang-Mills theory, and the terms for n greater or equal to 5 are secretly 0, but they are an elaborated 0. So they have this form, and when we impose Jacobi identity, we see that the additional terms vanishes. For example, here we have the 5-point correction, and imposing Jacobi identity, we see that this is actually 0. But when we compute the Feynman expansion, we have that the different contribution splits into different channels, and so together they are 0, but they cure the violation of color-kinematic duality for each channel. So after this, the introduction of this term, we have color-kinematic duality, but only for on-shell physical field. So we still may have color-kinematic duality violation coming from the unphysical polarization of the gluon and from ghosts. So to have a loop level color-kinematic duality, we want to discuss amplitude, where we admit as external states also unphysical gluons and ghosts. We may cure the color-kinematic violations coming from these fields, modifying the gauge fixing sector and the mechanical outdrop field and the ghost sector. So let's start considering scattering amplitudes. Let's consider scattering amplitudes with external arbitrarily polarized gluons. To compensate color-kinematic violation, we need to generate terms that are proportional to partial mu, a mu in the action. And this is possible in a recursive way. We can recursively generate this term with an appropriate choice of gauge, and so we redefine the Nakanishi outdrop field. For example, for Yang-Mills theory, the explicit correction for the Yang-Mills Lagrangian has this form here. Next, we have the problem of compensating for violation of color-kinematic duality coming from pair ghost-anti-ghost as external states. To compensate for that, we use on-shell world identity. On-shell world identity relates scattering amplitude with a certain number of pair ghost-anti-ghost to scattering amplitude with a lower number of pairs ghost-anti-ghost. In this way, we can relate the scattering amplitude we want to work on to scattering amplitude written in terms of bosonic field. And we modify in this way, in a recursive way, the ghost sector of the theory to compensate for color-kinematic violation. At this point, what we have is an action that generates color-kinematic dual parameterization of the scattering amplitude at 3 level and for on-shell BST fields. For example, for Yang-Mills theory, we don't need further correction at 4 point for pair ghost anti-ghost. So the only correction at 4 point for Yang-Mills is this one here. So we can strictify or the action that we obtain with this procedure introducing auxiliary field. And at 4 point for Yang-Mills, the expression of the cubic action at 4 point is that one. Now we want to bootstrap the color-kinematic duality of shell. So of shell, the violation of color-kinematic duality at this point may only be proportional to p squared, where p is the momentum of an external off-shell particle. So in order to compensate for that kind of violation, we need to generate terms that are proportional to the equation of motion of one of the fields. And in general, the needed field redefinition is non-local, as this f here, that is a degree n-1 polynomial in fields, and the derivative may contain terms 1 over box. So this is a non-local field redefinition. Non-local field redefinition are problematic if we want to use the standard scattering amplitude computation techniques with unitarity-based methods. And indeed, this transformation generates a non-trivial Jacobian determinant that leads to additional contour term that should be included in the perspective of renormalization. And the contour terms compensate for the violation of unitarity. But indeed, we may use at this point only standard Feynman diagrams computation. We will not rely on unitarity-based method. So at this point, we can strictify the Lagrange that we have obtained. We'll end up with a cubic theory. And we do this thanks to the strictification theorem. Now, we can do the following thing. Let's consider, for example, interaction term with 5 field. Every interaction terms may be linked to some trivalent tree topology that tell us how to strictify this term. We introduce auxiliary field that, when integrated out, to reproduce this term, and we can write an expression of this form as this is cubic expression here. In particular, we are grouping A and B into G1 and this A and D piece into G2. And if we integrate out the auxiliary field, we obtain precisely this quintic interaction term. And we can do the same for every term in a polynomial Lagrangian. And in particular, with auxiliary field, we can remove the non-locality of terms of this form here in the following way. If we integrate out the auxiliary field here, we recover this non-local term. So at the end of the story, we obtained up to the wanted perturbative order a cubic local action that manifests generalized color-kinematic duality. Now we want to link this procedure to a neutral homotopy structure that characterize generalized color-kinematic duality. So let's consider the L-infinity algebra associated to the action that we have obtained. This is a strict L-infinity algebra that's a differential graded Lie algebra, and it's factorized into a gauge algebra and a differential commutative graded algebra that represent the color stripped theory. And it contains a differential and the binary brackets of degree 0, mapping field times field to anti-field. Now, all the information about the kinematic algebra should be contained into this differential graded commutative algebra. So the fact that the theory is color-kinematic, is manifestly color-kinematic dual, should translate into some requirement for this differential graded commutative algebra. And this requirement is precisely that this strict C-infinity algebra can be upgraded, can be enhanced to a BV box algebra. Now, a BV box algebra is a graded vector space equipped with a Hodge tripole that is a tripole of endomorphism on this graded vector space. D is degree 1, H degree -1, and gray box is degree 0, that satisfy these relations here. Then we have a graded commutative product that is precisely the old differential graded commutative algebra product, M2. And we have a new product of degree -1 that is given in terms of the strict infinity algebra product and the endomorphism H. And the expression is that one. And we have all the technical requirements. In particular, this new product here, if we equip the degree 1 shifted graded vector space B with this product, we have a structure of a differential graded Lie algebra that is precisely the wanted kinematic algebra. So this is really the kinematic algebra product, and it's just shifted Lie bracket. So our statement is the following. A cubic theory that is manifestly color-kinematic dual, it is a color-kinematic dual theory if and only if we can factorize this theory in this way as Lie algebra and differential graded commutative algebra, and this theory is color-kinematic dual if and only if we can enhance the commutative algebra to a BV box algebra. Now, we want to use this framework to discuss double copy. In general, we should be careful, as BV box algebra contain in particular differential graded Lie algebra, and we don't have a general notion of tensor product between Lie algebras. Here in this table, I summarized the allowed tensor product for the classical algebras. So we need to be careful in defining the tensor product of two BV box algebras. But we take inspiration from string theory. So in string theory, the Hilbert space of closed string theory can be seen as the tensor product naively of the Hilbert space of open string theory. But the naive tensor product is too big. As we know, we should impose some condition on this tensor product, that is the section condition requiring that the allowed states have the same left and right momenta, and this is not enough. We need also the level matching condition. Now we can read this procedure in terms of Hodge tripole. For string theory, we have that the endomorphism D is the BST operator, H is B0, and the Virasoro zero mod is the gray box. We can mirror this procedure at the level of field theory, and in this way, selecting a differential graded Lie algebra as a subspace of the naive tensor product of two BV box algebras. So in field theory, in a standard field theory, the picture is the following. The endomorphism D is just the differential of the commutative algebra. H is a shift isomorphism. It just shifts the degree of the field, and then the gray box is just the wave operator. So we consider the naive tensor product of the two graded vector spaces, and we implement in the analogous way section condition and the level matching. In this way, we can select a diagonal subspace that is precisely a differential graded Lie algebra. And so we can associate Maurer-Cartan homotopy theory to this differential graded Lie algebra, and we call this theory the double copy, or using a new term, the syngamy of the two original theory. So we may generalize the notion of what a color kinematic dual theory is we say that a theory that admit decomposition in terms of the tensor product of two BV box algebra is color-kinematic dual theory. And we can consider left and right parent theories, color-kinematic dual parent theories, and we can recombine the left and right factor for these two theories using this Singami construction, and we can obtain in this way 4 new theories. So for Yang-Mills theory, the story is the following. We consider two Yang-Mills theory that maybe the same theory may be different as the left and right parent theory, here and here. The third theory that we obtain as Singamis are a theory of bi-adjoint scalar when we pick the left and right color part. This is just the bi-adjoint scalar theory. This is sometimes called the zeroth copy. Then if we pick the left color part and the right kinematic part, we obtain precisely the left Yang-Mills theory. Analogous thing, inverting left and right, we obtain the right Yang-Mills theory. And the most interesting Singami is obviously the one that we obtain when we combine the left and right kinematic parts. We obtain a theory that has the same field content of n equals 0 supergravity, and it is indeed perturbatively quantum equivalent to that theory. So this is just to summarize what we have said and what are the advantages of this formulation of color-kinematic duality and double copy. So we have a precise mathematical formulation of what color-kinematic duality is and what the kinematic algebra is, and we generalize with the notion of Singami the double copy procedure. And this provides us a Lagrangian incarnation of color-kinematic duality. And we have a natural homotopy algebra interpretation of this. Now, we want in general to discuss also theories that are not in a strictified form, that are the theory that we have before the strictification, or if you want, the theory that we have when we integrate out all the auxiliary field. They will be not cubic theories, and the natural algebraic structure to describe this theory is a generalization of BV box algebra that we call BV box infinity algebra, just like an infinity algebra generalized differential graded Lie algebra. As I said, when we considered the local field redefinition, we lost unitarity. So we cannot use for computation and proofs the unitarity-based method. However, the BV box algebra, the organization principle coming from BV box algebra and BV box infinity algebra structure may result in an advantage from the computational point of view, because for every number of external legs, we have basically one equation to check for color-kinematic duality. This is something that we still have to prove, the computational efficiency of this approach. So we don't have a final answer for this point. Finally, a very nice thing about this picture of color-kinematic duality is that we have a natural link with string theory. And this is good since color-kinematic duality and double copy, at least at tree level, comes from the KLT relation between open and closed string amplitude. So this is everything I wanted to say. Thank you for your attention.
Thank you. Okay. Other questions? Maybe I can start. Can you repeat the argument? So for a strictified, the statement was a strictified gauge field theory with L infinity algebra is color kinematically dual. If you split, you can write it as a tensor product between an algebra and a commutative strictified infinity. Yeah. Next slide, then 39.
Okay,
and
yes.
can be enhanced to a BV box algebra. Okay.
Yes, precisely. The fact that we can enhance the differential graded commutative algebra to a BV box algebra is equivalent to say that our cubic theory generates a color-kinematic dual parametrization of the scattering amplitude.
Okay, wow. And it's always clear that it's how to factorize into G and C.
Well, actually, the non-trivial point. So if we have a theory in a form that manifests BV box algebra, we are done. So the difficult thing in general is to produce the the BV box algebra for theories, to explicitly write the BV box algebra. This is not the non-trivial thing. And following this algorithm, we starting from a theory that manifests three-level color-kinematic duality, we can recursively obtain a formulation that can be read in terms of BV box algebra. This is the non-trivial thing. But once we have a factorization of a theory in terms of in terms of Lie algebra, in general, a BV box algebra, tensor, another BV box algebra, we know that the Feynman diagram satisfies color kinematic. The Feynman diagram expansion are manifestly color kinematic dual.
Okay, a loop level.
Yeah. This tree level, but then tree level implied this generalized notion of color kinematic duality for loops.
Okay, thank you.
Maybe I would have a related question. Is this factorization really unique, or can you do this job every time in a unique way? Factorize this algebra to the G and C.
Sorry, can you repeat your question? I didn't hear it.
Yeah.
Yeah. Okay. Thank you. Yeah.
As you described, you have some technology how you can factorize this algebra into L infinity with C infinity commutative algebra. Is this procedure giving you the unique factorization, or there is another kind of factorization of formal algebra?
Okay. After this procedure, this factorization here is just the color stripping. So just so this is basically at this point unique in the sense that we are just color stripping O theory. Yeah, this is the interpretation of this passage here.
Strictification example, it's not okay. The strictification, there is kind of universal strictification.
Yeah.
But yeah, you choose one which is best suited for you. Like for physics, you know.
Okay, the question was about the unique stratification. Okay, in general, stratification is not unique, yes. And basically, the color structure of the term you want to stratify tell you how to stratify that term. But yeah, in general, stratification is not unique. Once you have your stratified theory, then the color stripping is basically unique, the color stripping.
Yeah, maybe since nobody is asking further question, I would like to go back to the very beginning, maybe about BV. At the point where you showed that BV theory is equivalent to having an infinity algebra.
Okay.
Yeah. So, okay, what's happening here? So I thought, okay, QA on the first part should correspond to the BRST part, no? Because you said Q reduces to the BRST differential on the, or I mean on the fields, right? And on the anti-fields instead. What's going on?
Okay, so yes, PV differential on the BST field is just the old
Yeah.
BST. And you have that your gauge transformation and the equation of motion are parameterized by, are given in terms of QBV. So imposing a equation of motion, yeah, you obtain the full expression of your QBV.
Okay, maybe I'll ask in another way. So how is it possible to see in a very fast way that we have many products, the products for L infinity algebra, starting just from the action of Q on A, as in this slide?
So,
because for the fields part, if it's like a BRST, then yeah, as you showed from the first, in the first item here, you get structure constants, and therefore it's not an L infinity algebra, it's just a regular algebra. But then the anti-fields part, just
this is not for BST. So this is just a toy example where we have just ordinary vector space. So the BST is already a graded vector space. This is simpler. This is just ordinary finite dimensional vector space. And then in this case, the expression, the only possible expression of Q is this one. For the BST, is more complicated. Even at the BST level, I think it's more complicated than that.
Yeah, yeah.
This one. Yeah.
Okay.
Did you question why you have higher brightness as well?
Kind of how, yeah, how can
Well, in general, for BST, if we consider a high gauge theory and we construct QBST, then QBST does not square to 0. for higher gauge theory.
But you also have, I mean, because there's the Kussel resolution also, and there is also encodes the equation of motion. DRC is just a gauge transformation, but it has the equation of motion.
Right.
And from the equation of motion, of course, you then have higher brackets. So
Okay.
you have cubic interactions,
Okay.
so you have all of this very high bracket.
Okay. So even VRST is an infinite algebra.
Yeah, VRST is just a gauge algebra. So,
Yeah. Okay.
or rather the gauge algebra, right? Because you have this gauge algebra that
Okay.
acts onto the fields, and that gives you an infinity algebra, but the fields form a vector space with an infinity algebra. But then you expand by equational motion because you want to, you want to have the space of observers. You factor by gauge, you factor by equation of motion. VRC factors by equation of motion, and then you resolve by the equation of motion. VRC factors by gauge. You resolve by the equation of motion, and that gives you then this BV, the difference between VRC if you want to BV. Right?
Okay.
And the additional fields. Right? So you get Q on anti-fields gives you the equation for the fields.
Okay.
And so on.
Okay. Okay. Cool. Thanks. Okay, I think there are no more questions. We can thank you again. Yeah, thank you very much.
Yeah, thank you for the possibility to give a talk. Yeah, also remotely.
So